Okay, so to motivate both linear combinations and this term we're going to call span, I wanted to do an example of just a 2D example of this. So let's set a couple of vectors. Let's have v1 be the vector 3, 1, and v2 be the vector 4, -3. And first, let's think about linear combinations, right? So linear combinations are just any way the two operations we can do on vectors are adding and scaling, right? We can add and scale vectors. We can add vectors. We can scale vectors. And so if we kind of do all those combinations of both, we can start, those are called linear combinations. So any combining of these two operations. So linear combinations, so example, you could have something like, you could do something like 3v1 minus 4v2 or something like that, right? And that would be 3 times the vector 3, 1 minus 4 times the vector 4, -3, which if you do out the math, that's 10 minus 16, that's -6 on top, 3 plus 12 is 15 on the bottom. So that's an example linear combination. I could do something weirder, like I could do 1/10 v1 plus 1/100th v2 or something like that, and you could compute what that is. Maybe I won't bother doing it. Just any numbers. You could have, root 2 v1 plus pi v2 or minus pi v2, etc. Okay, but the kind of the more interesting question in terms of linear algebra is if I give you a specific vector, like say w is the vector 2, 5, you could ask the question, is W a linear combination of V1 and V2? Right, and so you're looking for, i.e. we want constants to put, we have these constants that we put in front of V1 and V2, here and here, or here and here, or here and here. Can we find constants to put in front of so that W is a linear combination of V1 and V2? And so, so in other words, i.e., can we find, and I'm going to use x1 and x2 just because it's kind of going to be the standard thing. Can we find x1 and x2 in the real numbers such that, all right, s dot t dot a lot for such that x1 v1 plus x2 v2 equals W? That's the question. Okay, and then you turn that into, I think you guys have probably seen this now already, but you turn this into, you plug in the actual values of V1 and V2 and W, and you get something kind of nice here, right? You get, we get something, the kind of thing we've seen before, which is a system of linear equations. 4, -3, and then that equals W, which was 2, 5. And this kind of becomes, on the one hand, you can make the x1, you can multiply, and scaling by x1 is like multiplying both the 3 and the 1 by x1, and scaling by x2 is the same thing, multiplying both those by x2. And then the addition, you just combine component by component. And so pretty quickly you see that this is 3x1 plus 4x2 here. You see this is x1 minus 3x2 here equals 2, 5. And it's a system of linear equations because you want the first entries to match in the second. And then you say, okay, well, in fact, that now I can write down an augmented matrix instead. So the columns are 3, 1, and 4, negative 3, which really, remember, notice are the vectors, v1 and v2. And this is, the column is 2, 5. So probably it's worth pointing out here that this is v1, this column is v2, and this column is w. And then you row reduce. And you could check it by hand or ask a computer. And I claim you get the following if you row reduce. I'm not going to go through this painstaking steps anymore. I claim you get this 2 there, negative 1 there. So that implies x1 equals 2 when x2 equals negative 1. And so yes, in fact, so the answer to the question back up here is yes. And in fact, we can write down explicitly, so w equals 2v1 minus v2. And by the way, it really is very satisfying to check this. So let's check to make sure that we agree with this. So v1 was the vector 3, 1. So 2 times the vector 3, 1 minus the vector 4, negative 3. And the first you double the 3, you get 6 minus 4 is 2. And then you get 2 minus negative 3 is 2 plus 3 is 5, and that's w. And so good, that feels good. So it really does work. I want to point out that you can actually draw a picture of this also. And so I have on the next page here, I'm just going to scroll down to the next page. So here are v1 and v2. And in fact, if I change the background of the paper, I can, I think, put the right grid on here. Maybe that one. Yeah, okay. So I actually drew this to specify it to the grid. So right here we have the I vector, which is the vector, the length 1 vector in the x direction. It's just the vector 1, 0. This is the vector 0, 1. This grid is the standard grid. So this v1 is 3, 1, because the tip is at over 3 up 1, and then the tip here of v2 is at 4, negative 3. And so we just said w was 2v1 minus v2, right? So that's a v1. This is another v1. That would make 2v1, right? Maybe it's worth writing there that this, if we did this vector right here, this would be 2v1 from the origin out. In fact, let me draw it. Yeah, that's 2v1. And then if we did minus v2, well, if you think about it, well, it's kind of off the page, but minus v2 would go the opposite direction of v2, right? Minus v2 would go that way. And so if we go from this point and go minus v2, oops, changed what I was, sorry. If we go minus v2, look, we exactly land on the tip of w. So we can think of, let me just use a different color here. We can think of this vector right here as, that's minus v2, right? Because the tail of it is right here and the tip of it is there. And so in fact, we land exactly at the tip of w. This point right here is, what you get if you go over 2 and then up 5. And so that's w. So that is 2i plus 5j is one way to write it. But then what we just showed is that we could also write it as 2v1 minus v2. Okay, so we can see it geometrically. And I just like this picture that you can sort of actually, okay, first we've checked the example geometrically, but the second thing I want to say is that what we've also done here, which I really like, is there's a deeper thing going on here. With the white grid is the standard, like the sort of the XY grid, the sort of standard grid that you make from the I and the J vector, right? Like every single side of one of these squares is an I and a J. An I, that's an I, that's a J, that's an I, that's a J, things like that. And this kind of shows you that I and J, linear combinations of I and J can generate everything, right? If I wanted to get to some point over here on the top left, I could, if I wanted to get to the tip of this vector, I could go some number of I's and then it's a fractional number and then some fractional number of j's, and I could get there. But then we have this purple grid, and the purple grid is sort of like the V1, V2 grid. And you can sort of see that I can get to lots of other places, right? Like I can get to, for example, this point. That would be 3V1 minus V2. This would be, right here would be V1 minus V2. You know, you can sort of go down the grid. You could say this would be V1 plus V2 over here. This would be minus V1 plus V2, this point. And you can also get points in the middle. Like if I wanted to get, let me just draw this on here. If I wanted to get sort of say to this point right here, the tip of this vector, I could say, well, let me go along the V1, V2 direction. So I want to go backwards along V1 until I'm kind of parallel to V2, right? And so you could have something like the following, where it's like, okay, maybe I go to there, and then if I go, that's parallel to there. And so, you know, maybe this is something like, I don't know, negative 2/3 V1. If this point's about 2/3 of the way from the origin out to negative V1, which is there, right? I'm going from the origin to there. And then maybe I'm talking about plus, let's see if I want to think about how far along of V2 I am here, it may also be about 2/3. Actually, that's interesting. So that's kind of an accident, but you could say it's approximately something like this, right? And so this is interesting because it looks like V1 and V2, linear combinations of that would also cover the entire plane. And that's going to be the whole purpose of span. And so let me just go to the next page and talk about span for a few minutes, just in this example. And then I'll do some more examples of more general things. So let me turn the paper back to get rid of the grid. Okay, so let me just talk about span for a few minutes. So this is a definition, the span of V1 and V2 is the set of all possible linear combinations of V1 and V2. It's a set. It has a notation. It's written as span of the set brackets V1, V2, like that. And it's defined, if you want to write it in set notation, you can think of it as the following. It's the set of everything of the form x1, v1 plus x2, v2, where x1 and x2 are real numbers. Right? And we just showed, for v1 and v2, this specific example, we just showed that W is in the span. W is an element of the span of V1 and V2. And it looks like the span of V1 and V2 is actually all of the R2 plane, the XY plane, the 2D plane. It looks like the span of V1 and V2 is in fact, just from that picture on the previous page with the sort of the grid lines, sort of can convince ourselves that we could reach any point on the plane. And so it looks like this is true. And so I actually will stop here and do the next video where I sort of justify more generally about what the span of two vectors is and show you, in terms of row reduction and what to look for in terms of pivots and stuff. But I just want to do this example first. So let's stop there.